So last week we talked about three different categories of time series methods, namely RNN-based models, convolution-based models, as well as transformer-based models. And for the next few weeks, we'll talk about some modifications on top of those methods to improve their forecasting performance. So today I will talk about those several techniques. The first technique is called window-wise normalization. Um, so here are some terminologies that we can look at first. So X will be our given variables and Y will be our target variables that we want to do the prediction for. And then K is the number of variables. So the idea is that um, when we are doing the forecasting, we have the context range as well as the prediction range. We should compute the mean and variance for each of those target variables based on the context range. And then we normalize the input values into the models using this mean and variance that we calculated. And then once we get our model predictions, we scale the predictions back using this mean and variance. And there's also some extra parameters such as the beta and also the gamma here. And those are all learnable parameters. But even if you set the beta to 0 and gamma to 1, the performance, you should still see an improvement in performance by applying this window-wise normalization. So I guess here, the main difference from just because for other traditional models that are not doing time series, most of the time you also need to apply this kind of normalization. And the main difference between the normalization that we do here versus other kind of normalizations is that here we do the mean and standard deviation based on each of the windows. So here's an example. So suppose say during training, the target variable has values range from 100 to 300. But at test, maybe the same target variable has range from 10 to 30. And we see that there's very different distributions during the train range versus the test range. And if you just input the raw values into the model, maybe you input the 100 to 300 into the model, and all of a sudden at test time, your model sees 10 to 30 instead of 100 to 300. Your model will no longer know what to do. So the idea is that after we do the normalization, maybe everything has mean of 0 and the variance of 1. And then during test time, your model will see the same set of mean and variance, and your model can perform more similarly as during the train time. And so here's the plot of the distributions of the range of values um, during training. And sorry, here is actually doing the model's input versus model's predictions. So in the first column is the distribution of values in the context range. So we see that for the train data and test data, they kind of follow different distributions. And after we apply this window-wise normalization and then plot the distributions again, we see that both the training data and the test data now follows a more similar distribution. And our model output will also follow a more similar distribution. But after we scale back our predictions using this calculated mean and standard deviation, um, our model will be able to predict different distributions for the train data and test data. And you might notice that this idea is also used in DPAR, but in DPAR, they didn't do those detailed analysis of those normalization techniques. So in the second semester, you'll be able to either keep working on the M5 dataset, or you can choose a research topic to work on. So maybe if you're interested in the research topic, you can um, try to train those beta and gamma parameters and then plot them to see what are those parameters that are actually learned for each data set. And second technique we'll introduce is called STL decomposition. So STL stands for seasonality, trend, and the residuals. So for a lot of the traditional statistical models, so decompose the raw time series into a trend component, which is so origin of time series is the top graph here. And then we can decompose it into trend, which is second plot, and then seasonality is third plot, and the residual, which is the last plot. So if you add up those three components, you'll be able to reconstruct the original time series. And if we're dealing with neural networks, maybe it's one way to extract the trend is by doing this average pooling. So last week we talked about convolutions, and if you apply a convolutional filter with ones everywhere in your convolutional filter, you're effectively just smoothing out the original time series. So if you apply a average kernel that's big enough, you'll be able to extract this trend component. And then you can subtract the trend from your original time series to get a set of residuals. And one idea is that maybe transformers are much better at interpolation. So for seasonalities or residuals, maybe the values will never go out, will most of the time will never go out of the range. But for trend, if in this case you have a increasing trend, then maybe we should use a separate model to handle the trend predictions versus residual predictions. And then maybe you have seasonalities that are maybe of a longer period. In some cases, if we just apply this average pooling, um, we'll misclassify them as trend instead of just long seasonalities. So maybe another idea is to do this trend and residual decomposition based on a longer window, so we can make sure that the trend we extract is actually trend rather than just some kind of long-term seasonalities. But even with just the simple average pooling, it's in fact still quite effective for a lot of the time series forecasting models. So we can apply this STL decomposition or this average pooling method to the transformer model or to DPR or to the convolution models that we talk about. And I think for quite a few of them, you'll see an improvement in performance. And third technique is called channel independence. So a data set might have many different target variables. And what channel independence does is that instead of predicting all the target variables altogether, maybe we can predict each target variable independently. And when predicting that target variable, we only look at the same target variable in the context instead of looking at all the target variables in the context. So one example is in the electricity data set. So the electricity data set is to predict the energy consumption of the 370 households. So instead of feeding in those 370 households altogether in the context range, maybe you only feed in whichever households that we want to predict. And it's important to note here that even though that in the context range, uh, we only feed in the same target variable as the one we want to do the prediction for. But across those 370 households, we still share the same set of weights for a neural network. So actually, if we think about DPR, it actually also apply this channel independence technique. So there are several benefits of applying this channel independence. So maybe different target variables, if we look at this electricity data set, maybe some households, they tend to plateau over the weekends. And for some other households, they might spike over the weekend instead. So having this separation of the target variables. So if the only inputting the same target variable in the context range will allow us to make the input less noisy. So the model can just focus on the relevant parts instead of also having to look at all the noisy parts as well. So this is a table of applying channel independence to a range of existing models. So each column will be a different model. So the first model is informer, and it adds a channel independence to the informer, and then autoformer adds a channel independence to the autoformer, and etc. And across those different evaluation data sets, this paper shows that channel independence actually improves the performance for all those models. However, if we think about applying this channel independence technique to real world data sets, there are some issues. In practical scenarios, most of the time we want to add do some feature engineering and add some features to the existing data set. But if we only look at the same target variable in the context range and also do the prediction for the same target variable, we will not be able to feed in those extra features into our model. So we can think about how we can add those extra features while making the input less noisy. And then the other issue is with those evaluation data sets. So I guess for most of those evaluation data sets, it's not really necessary for the models to look at the other target variables. So, for example, for this electricity data set, maybe to predict household I, it only makes sense to look at the past energy consumption from household I. It does not make sense to look at the other households. And also, if there's some other features that are helpful in the context range. Most of the time, there need to be a lag. So maybe we see whenever we see a spike in household J 24 time steps ago, we will see a spike in household I after 24 time steps. This kind of lag correlation um, will be necessary if we want to see an improvement in performance if we add in those extra target variables in the context range. But maybe this kind of lag correlation does not exist in those standard evaluation data sets. So maybe one other research topics that we can work on is to see how important those lag correlations are for each of those targets for each of those evaluation data sets. And then maybe you can also introduce a new evaluation data set to highlight this kind of lag correlation. And another modifications that you can do to improve the forecasting performance is how we can tokenize the time series. So if you already had a chance to look at the implementations I did for the transformer model, you might notice that right now each token is coming from a single time step. So if we look at the figure from the left, each time step will be a separate token. And when we do the attention, it might think that the two time steps or two tokens are very similar if they have the same value. But if we look at the figure on the right, we see that in reality, this smaller peak is actually having a more similar pattern to this larger peak at the end. So in that sense, each token should not just be based on a single time step. It should be based on multiple time steps. So one idea is to put more time steps into the same input token. So the number of time steps that we put into an input token can be called a patch. So if we have a patch size of 16, that means we put 16 time steps into every token. And then the stride is how many time steps we move to the right before introducing the second token. So here, every time every token has 16 time steps, and we move to the right 8 time steps and then define our second token. So by looking at more tokens or more time steps in one token, the model can see a improved have have a better idea of what's going on in the entire neighborhood instead of just paying attention to one single time step. And also, because transformers are prone to this memory issues, being able to merge multiple time steps into one token will allow the transformers to take in more time steps at once. And the figure on the right shows the changing performance as we change the patch size. you might actually notice that just the same ideas also applied in computer vision, where instead of operating on the raw pixels, the when we apply the transformer model to images, we will truncate the or divide the images into patches and then apply the transformer um, to each of the patches instead of to each of the pixels. So the idea is quite similar as it is for time series. And maybe one idea here is that instead of applying the same patch size to the time series, um, because there can be different seasonalities, maybe we can introduce different patch size and see if there's an improvement in performance. And the last idea I want to introduce is iterative forecasting versus direct forecasting. So iterative method is when we predict one step at a time and then feed our past predictions back into the model and then make the model to predict the next step again. And the disadvantage of doing this is that the error might accumulate from our past predictions. So if we want to do a long-term forecasting, we can apply this direct method. Instead of just predicting one step at a time, we can make the model predict the entire forecast horizon at once. And compared to the iterative methods, we'll see that the direct method will be much better for long-term forecasting. And another research idea here is that instead of applying this iterative method or applying this direct method, maybe we can iteratively predict multiple steps at a time. And then this can both allow us to do predictions for arbitrary forecast horizons, as well as avoiding the error accumulation issue in the vanilla iterative method. Okay, and this is the last technique I want to introduce today. Um, so you can go through those techniques I introduced today and then try to apply them to the vanilla transformer model or to other linear models or the RNN models and see if there's improvement in performance. And then you can also think about what are some additional modifications that we can do on top of those techniques to further improve their performance.